What we're going to do now, we're going to take a look at a couple of videos of a Stirling fan. And this Stirling fan is powered by thermal energy in the form of burning kerosene. And you'll see a little lamp that is lit at the beginning, or a lamp. It would be the device that would be similar to an old coal oil burning lamp. And it is providing the heat for the Stirling engine. And you'll also notice that I have to give it a little bit of a kickstart in order to get the fan going. But once it gets going, you can see the mechanisms, and you'll see the two piston cylinder devices working within the Stirling engine, as well as the regenerator within the middle. So let's take a look at that now. So that's the Stirling Engine in operation. You could see the working mechanism. It's kind of a complex working mechanism within the Stirling engine in order to execute the process itself. And what we're going to do now, let's take a look a little closer at what is going on within the two piston cylinder devices that are part of the Stirling. And so what I've done is I've sketched out 4 different steps, and those will correspond to the 4 steps of the process that we're looking at. In the middle, and the other thing that you'll see in the upper left-hand corner, we have the PV diagram for our reference. We can look back to it. This here, this is our regenerator, so I'm going to draw that red because it will denote the fact that it is retaining thermal energy as the gas moves from one side to the other. So what we're going to do, we're going to look step by step through our processes, and I will adjust the placement of the pistons for each of the particular steps that we're looking at. So let's begin with 1 through 2, which we said was an expansion process that is taking place at constant temperature. And heat addition is also occurring in that process. So heat addition is coming into our hot cylinder. So we have Q in here. And the other thing that is happening with our cold cylinder, this is fixed during this process. And it is fixed pretty much at bottom dead center. So it's at the lowest point that it can go. We're putting heat into the hot cylinder. We know that when you put heat into a cylinder, it is going to expand into the gas. So what happens is we have an expansion process taking place, but we are also doing work. And the net consequence of those two is that our expansion is taking place such that we maintain the temperature in an isothermal manner. And so the temperature is fixed at T hot during the expansion. The next step that we'll look at in our PV is going from 2 to 3, and that will be the constant volume process that we will show here. So what I'll have to do now is place my pistons within the cylinders so that they're at the correct location. To begin with, the hot should be at top dead center. So let's move this guy up. It goes up to top dead center, and the cool should be down at bottom dead center, which is where it was. So we're okay there. So it is at top dead center, and this is at bottom dead center. Now what's happening, this is a constant volume process. So that means that these two pistons need to move at the same rate, at the same velocity. So they're moving in unison. And while that is taking place, what happens is the working fluid then gets passed through the regenerator. And remember, it was hot because that's the hot cylinder. So it will be depositing thermal energy into the regenerator as it goes through. So that is step 2 through 3. And we can note here, heat into regenerator. So that's 2 through 3. Let's now look at 3 through 4. This is where we're rejecting thermal energy at a constant temperature. And the rejection will be from the cold cylinder. So this is going to be 3 through 4, and we refer to it as a compression process. So let me adjust the location or the positions of our pistons to make sure that they're at the right location. This one should be down at bottom dead center and fixed. So the hot is at bottom dead center and fixed. And the cold was up close to top dead center, and it's starting to come down. So it's starting to come down. We're compressing, and at the same time, what is happening, whenever we compress a gas, it gets hot. So we have Q out taking place, but we're doing this in a manner that it occurs isothermally, and so we're exchanging enough heat such that even though we're compressing the gas is also cooling, and the net consequence of those is that it occurs at a constant temperature. So what we can write here is that this is occurring at T low. This here was actually occurring at T hot. So I should write that in. Okay, so that is the compression process. And then the final step is 4 through 1. So if we look on our PV diagram, we're going from 4 up to 1. Again, this is another constant volume process where the gas will now come back through the regenerator, but now going in the other direction. So before I show which way the gas is going, I need to adjust my pistons to make sure that they're at the right locations. So the hot was near bottom dead center and it's starting to move up. The cold was near top dead center and it's moving down. And they're moving again in unison for this constant volume process. And so what's happening is the gas or the working fluid is now coming this way through the regenerator. And we can then write heat, actually I should say thermal energy, out of regenerator. So those are the 4 steps for the Stirling engine cycle. And so you can see that in order to implement this with a mechanical system, that is the Stirling engine, the crankshaft, and the connecting rods, it's a rather complex process because sometimes the pistons are moving and at other times they're not moving. And that's one of the tricks of the Stirling engine, is to make one that is balanced, has very low friction. It also needs to seal the gases inside. If we're dealing with helium or hydrogen, those are well known for leaking, and so you have to have very good seals. But if you have too good of seals, you're going to have a lot of friction. And consequently, it's a bit of a mechanical engineering challenge to build the Stirling engine. Where is the Stirling engine found? So the last thing we're going to do is close with by looking at applications. We talked about the heat engine, and so you can have like the fan that I showed you where you have fuel and burning underneath, although that was a kerosene fuel and it wasn't the cleanest. It was a little smelly, I must say. However, people have developed an environmentally friendly Stirling engine whereby you use solar energy to focus down on the hot cylinder. And Sandia National Labs developed one of these in New Mexico a number of years ago, and they would distribute them throughout different areas in New Mexico. But environmentally friendly solar engine. And this was Sandia National Labs. Another application, there is a company, I believe out of New Zealand, called Whispergen, and they were making a system, they still may, I'm not sure what their status is right now, but they were making a system to heat domestic water and also generate electricity. And this obviously would be something that would burning methane, so you have internal combustion, but again it's operating like an external fuel engine. Now another thing, if you reverse this cycle and you put work in, the Stirling is actually a really good refrigeration system, and it's even used for cryogenic cooling, so you can cool things down to very, very low temperatures. Now that's not a heat power cycle, but I just mention it because it can be used for cooling, and that could be used for, it's lightweight refrigeration essentially, but it could be used for cooling electronics that are sensitive to thermal noise, for example. Cooling And this obviously would be an application that would require you to have very lightweight and compact refrigeration. So that would be compact refrigeration. But that's not what we're looking at. We're looking at the power cycle, but I just mentioned that as it's another application of the Stirling cycle. So that is the Stirling cycle. That will conclude today's lecture. I'd like to thank you for your attention, and we'll see you next time. Thank you. Bye-bye.